Hi, my name is Kelsey Doerksen, and I'm the president of the Carleton Planetary Robotics Team. We are a team of engineering and science students from Carleton University in Ottawa, Ontario, building and designing Mars rovers, and we've entered to compete at the 2017 University Rover Challenge.
The rover's power source is lithium iron phosphate batteries rated at 700 watt-hours. They can provide over an hour of runtime for the Extreme Retrieval and Delivery Challenge, which is anticipated to be the most power-intensive challenge of the competition. The power distribution is done via a star topology with 4 power rails, 2 of which are dedicated to motion, 1 is dedicated to computing, and the remaining rail is dedicated to communications.
The rover communicates using 2.4 GHz Wi-Fi and has a folded dipole antenna mounted on the mast for omnidirectional communications, even when the rover is tilted by more than 45 degrees. At the base station, we use a 24 dBi parabolic antenna mounted on a custom pan-tilt mechanism. The base station antenna system knows the pose of the rover and itself and autonomously steers to maintain a connection. The rover will carry several single-board computers and a single microcontroller for handling real-time tasks. The intensive processing required for autonomy will be managed by an Odroid XU3 with 8 onboard ARM cores.
The software architecture on our rover is designed to scale horizontally, which is ideal for continuous integration and development without any performance loss. Currently, we have 4 microcomputers on our rover controlling all of the systems, which are connected through a distributed network. This year, the role of the software team has greatly expanded due to the autonomy task. We decided to use the stereo camera, which will allow for depth perception similar to how human eyes work. The stereo camera, combined with numerous other sensors, will allow the rover to monitor its environment and its position within it using the SLAM algorithm. The rover will also move towards a set of GPS coordinates using Dijkstra's algorithm, and it will avoid obstacles along the way.
Our software is based around the robotic operating system. Within this framework, we will be using multiple C++ and Python programs to communicate with the base station, interface with the hardware, and control the rover. The base station will open a WebSocket to communicate with the rover, allowing us to continuously monitor subsystems and issue commands to the rover with low latency. We carefully manage network usage in order to reduce data transmission. This allows us to say less and do more over the limited and potentially volatile network connection.
Communications is the only mechanical subsystem with work on and off the rover. On the rover, a simple mast will be used to mount the communications antenna, the GPS, and a wide view camera. At the base station, a 2-axis motion system will be used to steer our large antenna. Steered automatically using the GPS location of the rover, the antenna will point at the rover, allowing for constant communication for line-of-sight operations.
The mechanical team is divided up into 6 different subsystems: the arm, claw, chassis, communications, frame, and science. This provides the arm with adequate strength for lifting objects during the astronaut assistant task, while creating a highly accurate zero backlash system for object manipulation during the equipment servicing task. The frame is the main body of the rover and houses all electrical components. Built using T-slotted 20x20 aluminum channel, the frame is strong and lightweight, while also being highly modular and allowing for any design changes to be accommodated.
The science team is responsible for providing solutions to all things related to the science cache task. The onboard sensor used on the rover is the Decagon 5TE soil moisture, temperature, and electrical conductivity sensor. This has been integrated into the drill mechanism design in order to take the 3 onboard soil measurements for the science cache task. The 5T sensor is connected to Arduino that will then output real-time data to the command station computer consisting of the soil temperature, moisture, and electrical conductivity. Soil samples from the Utah desert area have been collected so that we can take preliminary measurements and compare them to those that we take during the competition. A camera mounted on the rover's mast will be used to take the panoramic photo such that we can analyze the stratigraphic columns found. A high-definition camera will be mounted to the drilling mechanism so that we can take a close-up of the sample site as well as the drilled hole. Repeated soil moisture and electrical conductivity measurements will be taken, and an additional pH level of the soil will be determined using a sensing probe.